Right, good evening. This is the third lecture on the statistical series. For this lecture, we will be talking about statistical testing, right? And this will be just a review or also be an introduction to the tests that we do in statistics, right? Now, basically, statistical testing is about making comparisons on samples and then eventually getting a definitive yes or no answer, okay, depending on the statistical parameters that we get. And this is basically a choice between accepting or rejecting the null hypothesis or the alternative hypothesis. Right? For example, we are talking about three samples of gold ores in the same exploration area, and we got so these are samples consisting of multiple observations, and their means are different. For example, say 2%, 3%, and 1.5%. As long as we know the number of samples and the other statistical summary statistics like standard deviation, we can determine if these samples come from the same population or not. And of course, that has implications on the exploration. Okay. All right. Now let's talk about hypothesis. Hypothesis, plural. All right. Null hypothesis. One good example of that is as shown here. You have mu one and mu two, and yeah, this is our null hypothesis. And basically, the opposite of your null hypothesis is your alternative hypothesis, and it can go many ways. So the alternative hypothesis can be that mu1 is not equal to mu2. It can also be stated as mu1 is greater than mu2. Okay? And this basically this example is what we call a two-sided test. So you have because the alternative hypothesis concerns the side where mu1 is actually greater than where mu2 is greater than mu1, and also concerns the other side where mu2 is less than mu1. Okay? So so this mu1 is not equal to mu2. Okay? Can basically split into two sides. Okay? Example B here is what we call a one-sided test because we only care about one side. Okay? Basically, we only care about the values where mu1 is greater than mu2. Okay? All right. Now let's talk about the possible outcomes, okay, on how we can interpret your null hypothesis. Okay. Now remember that accepting a hypothesis doesn't mean that it is 100% correct. There's always a chance that uh, that you may end up accepting a null hypothesis, but it might be incorrect. And here we have four possible outcomes. Right, first is your upper left outcome, where it's sort of a true positive scenario where you accepted the null hypothesis, okay, and the null hypothesis in fact is actually correct. Okay, okay. So this outcome has a probability of occurring. Uh, you can calculate it as 1 minus alpha, where alpha is the level of significance. Okay? I'll discuss it. I'll talk about that later on. Second outcome is your upper right. Okay? This is sort of your false positive, okay? Where you accept the null hypothesis, but the null hypothesis is actually wrong. Okay? And the probability of making this kind of false positive is what we call a type 2 error, and its probability of occurring is expressed as the probability of beta, or a beta value. Okay, so we have alpha and beta, but for for our purposes, we will be mostly talking about the alpha values. Going back, we have the lower left value, where we reject the null hypothesis, but in fact, the null hypothesis is actually correct. Okay? So this is sort of a false negative scenario. Okay? So we rejected the null hypothesis, but it's actually correct. And the chances of this one occurring is equal to the probability of A, or the level of significance. And finally, we have the sort of true negative scenario, where we reject the null hypothesis, and the null hypothesis in fact is incorrect. All right, slide. Now I think you saw there how phrasing the null hypothesis can change the outcomes, or our interpretation. Okay, so choosing the null hypothesis, or how we phrase our null hypothesis, is actually important. This will influence our actions. Okay? As you will see here, let's see. So let's say our level of significance, alpha, okay, is 5%. Okay? And this translates to 100 minus 5. You get a 95% confidence level. Confidence level simply means that we are 95% correct. Okay? You have a 95% chance of being correct. Okay? Now, now let's have an example. Okay? Our example is environmental cleanup, okay, where we have a potentially contaminated site, and the choice of null hypothesis will influence the outcome of our actions after we do the statistical testing. Okay, so we have here two cases on how we can phrase the null hypothesis. So we have case A and case B. Now for case A, we phrase the null hypothesis as follows. The site is actually clean. Okay? So it has no contaminants, so that's our null hypothesis in case A. In case B, the site is contaminated. Okay? Basically, these are two opposite statements. Now let's look at case A. Okay? And note, in statistical testing, we mostly operate only on the left column. So if you remember the previous slide, you have another column here, okay, where we talk about the beta values. But for our purposes, we'll be just talking about the left-hand column. All right, so we have two possible outcomes in scenario A. If we accept the null hypothesis, okay, there is a 95% chance that the site, in fact, is actually contaminated. Okay? Or sorry, is actually clean. So since this is a good scenario, okay, because you don't actually spend money cleaning up the site, and there are actually no contaminants that will harm people. So the other possible outcome is where we reject the null hypothesis. Okay? So we say that the site is not clean, and in there we have a 5% chance, okay, that the site is actually clean. Okay? So we're kind of wrong here. Okay? And the consequence here is bad, but not really so bad because in here we spend some money. Uh, we spend money to clean up the site, okay? When in fact there are actually no contaminants in the site. Okay? So we basically wasted money. Okay? Now let's talk about the scenario case B, okay, where we phrase the null hypothesis as site is contaminated. Okay? Now again we have two outcomes here. If we accept the null hypothesis, there is a 95% chance that the site is actually contaminated. Okay, so this is good because okay, so we interpreted that the site is contaminated and it is actually contaminated. So we do some cleanup. We spend some money cleaning up the site, and we actually remove, okay, the contaminants in the site. Okay, so it's a victory for us. Now the other outcome here is we can we also can end up rejecting the null hypothesis. So we say that the site is actually clean, but there is a 5% chance that we are wrong here. Okay, so so what happens if we are wrong? So we declare that the site is clean, and there's a 5% chance that we are wrong. If we are wrong, we end up doing nothing, and we end up leaving the contaminants in the site. Uh, People can get sick, and this can have consequences, like legal consequences. Okay? If you're a like a for example, if you're a landowner, and possibly some reputational consequences if like you're a consultant. Okay, so you're a consultant, you made some bad decisions. Okay, that would be trouble. That would be a big trouble for your career. Okay? So at least we can see here how phrasing the null hypothesis can affect the outcomes of our actions, okay, on a given problem. So we can see here in most scenarios, it's actually fine to spend some money, uh, even if even if our interpretation is wrong. I mean, we spent some money cleaning up the site, even if it's actually not contaminated. I mean, that's more acceptable compared to the consequence in case B, where we declared the site as clean when in fact it was actually contaminated. So it boils down to the values, okay? And it also boils down to the consequences of the of our actions, no? On how we act upon the results of the hypothesis testing. Sorry. Okay, so I would emphasize that this is really relevant when you're talking about managing risks For example, you're working in the industry or you're uh, trying to solve actual problems, it is best to state the null hypothesis in both forms first, okay, like what we did here, and then assess, okay, what would be the possible outcomes if we accept or reject the null hypothesis. Now, let's have a more practical or fun example. So let's say you're infatuated with a certain person, or basically you have a crush on a person, and let's say null hypothesis A is that your crush likes you back. The person you like likes you back. Now, let's talk about the consequences of our actions here. If you accept the null hypothesis that your crush likes you back, you have a 95% chance of being correct. Okay? So it's good. You pursue the person you like, and he or she likes you back, and basically you're successful with your romantic life. Now, if you reject this null hypothesis, there is a 5%. So basically, you reject the null hypothesis. You basically say that I think the person doesn't like me back, so we go with that. There's a 5% chance that the person actually likes you. Okay? So it's quite sad. You end up not pursuing. Sorry. All right. So it's quite sad. I mean, you end up not pursuing the said person, and you, given that the person actually likes you, and you'll also never know the answer, okay, whether the person likes you or not. Now, let's do it on another phrasing. Let's say, uh, let's phrase the null hypothesis on the other way around. Let's say that the null hypothesis is that your person of interest doesn't like you back. So if you accept this null hypothesis, so you accept that the person doesn't like you have a 95% chance of being correct, right? So it's good. You end up not pursuing the person who doesn't like you anyway. Okay, so that's the outcome number one. Outcome number two is if you reject this null hypothesis. Okay, so you say that, fuck it, man. I think this person likes me. You have a 5% chance that the person actually likes you. Okay? Uh, the person actually doesn't like you. So you pursue the person, but you get rejected in the end. Okay. So at this point, you can look at both scenarios of how we phrase the null hypothesis, and it's really just a matter of the choice is really just a matter of your values. I mean, in this scenario, which do you value more, your pride, or do you place more value in knowing the truth? Okay, so it's not really straightforward. So choosing the null hypothesis is not really a straightforward a situation. And you have to really account for the consequences of the actions arising from the result of the test. Okay, so that's how we deal with the null hypothesis in a problem solving or a practical scenario. But if you're just talking about the academic way of using null hypothesis, like you're doing a thesis or you're doing science research, but uh, the default phrasing is like this: the alternative hypothesis is gonna be basically your new idea or your hypothesis, basically your scientific hypothesis, the idea that you're trying to push, while the null hypothesis will be the prevailing idea or the old idea or the generally accepted truth. Okay, so I hope that clears the nuances of null hypothesis. All right, let's talk about partition. Basically, how we partition the values to accept and reject. Okay, and this, of course, will depend on the level of significance or the alpha. Okay, level of significance is a statistical term for expressing, okay, how willing you are to be wrong. Okay? So if you choose like 5% alpha or 5% level of significance, it means that you can tolerate 5% chance of being wrong. Okay? If you choose an alpha of 10%, it means you can tolerate 10% chance of being wrong. Okay? If you're really like meticulous, you can choose like 1% confidence level of significance where you can only tolerate 1% chance of being wrong. Okay? Now, we can also express that chance in a more in a positive in a in a positive way. We have what we call the confidence level. The confidence level is basically um, the chance of you being right. Okay? So basically, confidence level is just 100 minus your level of significance. So if you have a level of significance of 5%, you have a confidence level of 95%. Okay? All right, now generally the lower the confidence level, the wider the acceptance zone. Okay, so you're basically tolerating more errors when your confidence level is low, like for example 90% confidence level. That equates to level of significance of 10%. Okay, so it will have a generally wider acceptance zone. You have a lower standard for for accepting the null hypothesis. Okay. Now, just note that this drawing is what we call a right-tailed test because the area of rejection, the values to be rejected are in the right hand, while this drawing below is what we call a two-tailed test because you have rejection areas on either sides of your test values. Right, now let's talk about the statistic. Okay. Okay. We have here what we call the p-value. Basically, it's just a measure of the probability that an observed phenomenon stated in the alternative hypothesis could have occurred just by random chance. Okay? So basically, p-value is your okay. Basically, the higher the p-value, the bigger the chance that the stuff that you're pushing for in the alternative hypothesis is basically just due to random chance. Okay? So the higher the p-value, the weaker the support for the alternative hypothesis. Okay, so when you have large p-values, it means the evidence supporting the alternative hypothesis is not statistically significant, or basically it's just due to random chance. So in this case, we cannot accept the alternative hypothesis, and we stick with the null hypothesis. Okay? So so we basically fail to reject the null hypothesis. All right, now we have saw about the sampling distribution. Okay, so basically this is just the range of values and their likelihoods for a given population. Okay, so basically if you want to find the average value of something in a large group, okay, but basically it's not always practical to test or observe the whole group, so you can basically just use a distribution to make a guess on what would be the most likely values, okay, will you encounter. For example, you took 10 samples or samples. So each or sample consists of 5 measurements of percent gold content in a porphyry copper site. Okay? And of course, each sample will have a slightly different mean value since the actual values will be somewhat randomly distributed. And the sampling distribution is just a graph of probability versus the mean values. Okay? So let's say, for example, the true mean or the population mean is around 2% gold. Okay, so that's the percentage of gold in general for the whole population of the porphyry copper. Now, it's really unlikely that you will get an ore that has 80% gold, but getting numbers that are closer to 2%, okay, like 1.5% or 2.5% gold is actually more likely. Okay? And we can use the distribution, the sampling distribution, to basically guess how likely will these values occur. Okay, now per type of statistical comparison, we use different shapes of sampling distribution. For example, for the comparison of two means, okay, when you're testing two means, we normally use the standard normal or the standard Gaussian or the t distributions or the student's t distribution. For the comparison of variances or basically the scatter of your data, we normally use the F distribution. Okay? And we can also use the x squared distribution, right? All right, now let's talk about again have a review on the probability and the p-values. Okay, so here we are comparing two means, right? So we use the normal distribution, which is also called the Gaussian distribution. And here we can see in the y-axis that we have your probabilities. And then in the x-axis, uh, we have here your, this is actually not mean values, right? These are actually z-scores. Okay? I'll talk about that later on. Okay, so z-scores, I'll explain that later on, but basically just accept the numbers that I'm gonna spew out. So for example, our z value is 1.28. Okay? So this will plot here. Okay? So z-score 1.28. If we plot that in the distribution curve, we get a number that's all right. This is quite tricky because when we are calculating the p-values on a Gaussian distribution, we actually have to take the cumulative probability. So we actually have to basically, this is where 128, you basically have to integrate the whole area behind it. Okay? Okay, so this part is actually 90% cumulative probability. On in the right side of it is 10% cumulative probability. Okay? So since we are on a right-tailed test, okay, you can see here that the probability of the cumulative probability of 1.28 is actually zero point 0.1 or 10%. All right, now let's move on, or let's zoom out a bit and talk about the statistical testing procedure. Basically, step one is you select the null hypothesis, or H naught, and the alternative hypothesis, or H1 or HA. Okay, so again, as discussed earlier, in traditional statistics, the null hypothesis is opposite the common, is basically just the common, opposite the commonly accepted hypothesis. Or in the academe, the null hypothesis is just your prevailing thinking, and then the alternative hypothesis would be the new idea that you're pushing for. But again, as discussed earlier, if you're doing statistics to solve actual problems, you will have to phrase the null hypothesis, okay, based on the consequences. Okay? Right. Step two is to choose the appropriate statistic. This can be mean, variance, or distribution, okay, depending on what we are comparing. And then three, we set the level of significance, or the alpha. Note again, the higher the level of significance, the greater the chances of error. Okay. Or I mean, the larger the value of level of significance, the larger chances of error. For example, if our alpha is 10%, that would have a larger chance of error than an alpha of, let's say, 5%. Okay? But the most commonly used alpha value is 5%. Is 5%. Okay? And then step four, we evaluate the statistic for the case of interest, the ZS, or the Z-score. I will be discussing Z-score later on, but for now, the Z-score is representing your mean. Okay? For example, our example here is mean. And and after getting the Z-score, we basically plot the value uh, on the sampling distribution here. Okay? So this is our Z-score. Okay? And then we get the, okay? And then we can we also plot the Z alpha here. Okay? So we first start with the alpha, and then we look for the position of the Z alpha such that the area here, if we integrate it, okay, the area here would be equal to 0.05 or 5%. Okay? So so alpha is 5% cumulative probability. So we superimpose it here. This would be the approximate position of your Z alpha. Okay. Then we compare the Z score versus the Z alpha. And since this is a right-tailed test, if the p-value is bigger than the alpha, we fail to reject the null hypothesis, and we get to keep the null hypothesis. Okay? All right, so the p-value is here. Actually, it depends actually on the test here. So the the ZS here is left of your Z alpha. So in here we actually accept the null hypothesis. Right now, let's talk about parameter testing. Um, Specifically on how to test two different means. Okay. So again, let's have a recap on what is independence. All right, so independence simply means that knowing the result of one event does not change the probability of the unknown outcome of the other event. Okay. So for example, if you have two events, A and B. Okay, so if they are independent of each other, uh, their probabilities should be as follows. So if for so we have two probability events here. So this one is probability A were, that A will occur given that event B has occurred. On the right side here is the probability of event A occurring. And you can see here that the two events here basically have the same probability values. Okay, so you can see here that the occurrence of event B did not affect the probability of event A. Okay, so that simply means that A and B here are independent. Okay, so so let's have more concrete examples here. So you're so head and tail flips, right? So if you're tossing coins, the previous result doesn't affect the next result. Okay, so they are independent events. Now, if you have a deck of cards, okay, and for example, you took one king card, okay, and you did not put back the card of king, okay, okay, so the chances of getting another king card, of course, will actually change, okay. So the first event actually influenced the next event, okay, because you generally modified the deck of cards from which you're drawing you're drawing a card. Now, let's talk about testing parent populations. Okay, so this testing is just a subset of what we call the one sample t-test. Okay? In a one sample t-test, the test variable's mean is compared against a test value, which is a known or a hypothesized value of the mean in the population. Okay? So you basically know the actual or the hypothetical value of the mean of the population. And you just want to know if the value that you have is more or less same or within the value of the mean of the population. Okay, so the mean of the population can either come from different sources. It might come from literature review, so basically the science journals or research, or basically you have a trusted organization that is specifying the acceptable values, or basically it could be a legal requirement or an industry standard. For example, in the U.S. Environmental Protection Agency or the EPA, they have set clearance levels for the amount of lead present in homes that are acceptable. So the amount of lead in homes should not be more than 10 micrograms per square foot. Okay, and basically you can measure, you can just go to a random home and measure the said amount of lead in that house, okay, and compare the value that you get against the EPA standard. Okay. So in here, your measurements actually form the value of the sample mean. Okay. So your measurements are is the sample, while the EPA standard, the EPA acceptable standard for lead content is your population mean. All right, and you have here an example of a one-sided test, uh, a specifically a parent population test that is one-sided. Okay? And here you have a right-tailed test, which means that in the null hypothesis, the sample mean is less than the population mean, or less than or equal to the population mean, and we will reject the null hypothesis if the sample mean is bigger than the population mean. Okay. All right, I'm just gonna skip this part. Okay, so we just need the central limit theorem for the calculation stuff that we're gonna do. But for now, let's jump here to the standard normal distribution. This is the z distribution and z-scores that I was talking about earlier. So again, this is the standard normal distribution. It is also called the z distribution. It is a special normal distribution where the mean is 0. Okay, so the central part here is 0, and the standard deviation is equal to 1. Okay, so if you remember the Gaussian distribution, the classic Gaussian distribution is that 95% of all the data will fall within plus minus 2 standard deviations. Okay? So you can see here, this is a this is still a Gaussian or the normal distribution, because you can see here a significant your 90 the 95% of your data is contained within the bounds of your negative and positive two standard deviations. All right, so again, going back to the standard normal distribution, it is basically a plot of your z-scores. Okay, so these are your z-scores, okay, which are basically your standard. These are units of standard deviation. So z-scores versus your probability, f of z. Okay, so any normal distribution can be standardized by converting its values into z-scores. And z-scores tell you how many standard deviations from the mean each value lies. Okay? So if your value or your mean plotted in here, let's say 1, this means that your value is 1 standard deviation away from the mean. Okay? So that's how you read a standard normal distribution plot, right? So if your value is -1 or your z-score is -1, it means that your statistical parameter has a value that is 1 standard deviation away from the mean, right? So note, all right, I discussed that earlier. Okay. So yeah, so basically, this figure is basically just a normal distribution graph, okay, where the values are just divided by the standard deviation. So you're just trying to normalize the graph by the standard deviation. All right, we have here an example of a one sample t-test. Right, now the null hypothesis here is the sample mean. And all right, so the null hypothesis again states that the sample mean is less than or equal to the population mean. Okay, so this is your sample mean, and this is your population mean. Okay, so in the curve here, we only care about the values on the left. Okay, so if the values are on the right, okay, we will reject the null hypothesis. Okay, so this is what we want. This part we don't want. Okay, so when so this is a right-tailed test again because the rejection values are on the right. All right, so now the alpha or the significance level or the level of significance is 5%. Okay, so this is the standard value, or this is the most commonly used value. Okay, and so that means we have a 5% chance of making type 1 errors. All right, so going back, we calculate the z-score by using the transformation equation, which is basically based on the central limit theorem. And what we do here is we just subtract the sample mean by the population mean. So this is the sample mean, and then we subtract the population mean value, and then we divide it um, by the population standard deviation and by the square root of the inverse of the sample size. So this is basically the standard deviation. Okay, so this is your standard dev. Okay, and we get this value. So 1.25, we plot it here. All right, 1.25, and then we look for the part of the graph where the cumulative probability is 0.05. This is that region. Okay. So we see here that the rejection area, or rather the z-score here is not inside the rejection area. So we get to accept the null hypothesis. Okay. So that's how the testing of two means work. Okay. All right. Just note that the sample size can affect the acceptance of your null hypothesis. Okay. So note here we have basically the same population. So these came from the same population, but we have different sample sizes: 10, 25, 100, 250. And again, as a result, you will get different z-scores here. Okay, 0.79, 1.25, 2.5, and you will get, of course, also different p-values here corresponding to your z-scores. And note, all right, that so we have here your level of significance, which is 5%. And note that the lower sample sizes were accepted here. Okay? So, so just note in general that larger sample sizes are, of course, always preferred. Okay? This is normally what we want. Okay? We prefer larger sample sizes. The closer the variance of the sample to the variance of the population, the better. Okay? And of course, the way to deal with this is to make sure that we are getting enough sample size, we're taking enough samples, and at the same time, we are representing all the spectrum of values within the population. So we try, as much as possible, we try to capture the small, medium, and big values within the population. Okay, to ensure that the sample variance or the scatter of the data within the sample is more or less similar to the scatter within the population. Right now, let's talk about the degrees of freedom. It sounds complicated, but basically, the degrees of freedom is related to the uh, number of the sample size. Okay? More or less, it's just really related to the sample size. All right, students T distribution. So you saw earlier that we were working with the standard Gaussian distribution. Oh, sorry, the normalized standard distribution, which is also called the normalized Gaussian distribution. Now, if our sample size is quite small, or we have limited information on the mean and variance of the population, we can use this students T distribution. Okay? So basically, this is just like a Gaussian distribution, but with some special features that allow us to work with data that has a very limited um, information. Okay? So students T was invented by a I think beer brewer or a beer brewing quality checker. Okay, so this person wanted to remain anonymous with his publications, so he published his statistical methods under the name student. Okay, his pseudonym was student, and he basically invented ways to check the quality of beer ingredients by only taking a few observations. Okay? So I presume the tester did not want to get drunk by drinking a lot of beer samples or probably something similar to that. But the important stuff here is that students T is basically a way to capture the distribution of your data by taking only a few observations on a sample. All right, so this distribution basically describes the standardized distances of sample means to the population mean when the population standard deviation is not known and the observations come from a normally distributed population. So still again, this is only useful for a data or a population that has a normal distribution. A little bit more student C distribution. Okay, so yeah, it's basically substituted for standard normal distribution when you have like small sample size, like you have less than 30 observations per sample, or again, you don't know the statistical parameters of the population. Okay, so to compensate again for the uncertainties due to the small sample size and unknowns in the population, students generally tends to have wider tails than a standard normal distribution. Okay, so generally its plot is more or less wider, so it makes room for more extreme values. Okay? Okay, so you have here examples of t distributions. So k here is your degrees of freedom or the number of samples, right? So you can see here the width of the plot is plus minus 5 standard deviation. So if you remember the Gaussian distribution or the normalized Gaussian distribution is around negative plus minus 3.5 standard deviation in width. Okay, students T is like plus minus 5, so it's wider. All right, variance testing two variances. Again, if you will remember, variance is a measure of spread of data around the mean, basically a measure of the scatter. The idea of testing two variances is basically to compare two groups, okay, where we define one group as a sample that is coming from one population, and the other group is another sample that's also coming from a different population. So two groups, we're talking about two samples that are coming from totally different populations. So like we're literally comparing apples and oranges here. Okay? And the use of regression, the use of comparing two variances is commonly done in regression. Okay? Or in regression, we're trying to observe the relationships between two samples. And remember, in regression, we are trying to extract the relationship between the two groups or the two samples, and it's going to be expressed as an equation. But remember, or the way to optimize a regression is by minimizing the variance between the response variable or the variable that we are trying to predict and the predictor variable or the variable that we are using to predict the other variable. So basically, the dependent and independent variables should more or less have a similar variance when we are doing a regression. Okay, and this method is used to check if the two variances are the same or not, statistically speaking. All right, now let's talk about the F distribution. So again, comparing two variances, this involves computing what we call the F statistic, which is then compared to the F critical, and they function similarly as how we compare the p-value to the alpha value when we're doing the testing of two means. So in the testing of two variances, we are comparing the calculated F statistic versus the F critical. Okay? So the F statistic is what we calculate from our data, and then the F critical is the threshold value for accepting or rejecting the null hypothesis. Right, so generally we have a collection of F statistic values that are plotted against probability. So when we have a collection of F statistic values and we know their probability of occurring and we can plot it, we call it an F distribution. Okay, so This is basically just the counterpart of your t distribution or the student's t distribution for testing of means. F distribution is just used for testing of two variances. And F distribution is generally calculated from the sample standard deviation and population standard deviation of each groups. Basically, an F statistic or an F value, basically the general formula is you just take the standard deviation or the sigma, like sigma one of your one group, and then divide it by the standard deviation of the population of the group one. Sorry, so this is sigma, standard deviation, and then divide it by the standard deviation of another group, of the sample of the other group, which is also divided by the standard deviation of the population of that group. All right. For calculation purposes, the standard deviations of the population are equal to 1, so they just cancel out. So we are just left with F statistic is just, so F stat is just equal to your standard deviation of group 1 divided by the standard deviation of group 2. Okay. Okay, so skipping this one. And yeah, we have an example here. We have two groups represented by sample 1 and sample 2. So these are two different, these are coming from two different populations. So these are your this is your apple and your orange comparison. And we just want to know if their variance is the same. So that is our null hypothesis. The null hypothesis actually is sample 1, or the va variance of sample 1 is just equal to the variance of sample 2. And that's our null hypothesis. So what we do is we just take the largest variance. So this is the largest one from sample 1. Okay. Sorry. I think I discussed previously that the F statistic is calculated by dividing standard deviation by other standard deviation. I was meaning to say variance, right? Sorry. So this, so again, going back, we take the largest variance and then we divide it by the smaller variance to get the F value. So here it's 2.24. So the practice of dividing the larger variance by the smaller variance, this is done for practicality purposes. Okay, it is done to force the F test into a right-tailed test, which is much easier to calculate than a left-tailed test. So this is, again, this is a right-tailed test. You have your rejection area here. And then we calculate the F statistic by dividing the sample 1 variance by sample 2 variance. Again, so we did that. Check. And then we construct an F distribution curve based on the degrees of freedom, which is basically just the sample sizes of the two groups minus 1. You can see here that the sample size of group 1 is 11 and group 2 is 26. To get the degrees of freedom, we just subtract 1 from them. So So the degrees of freedom of sample 1 is just 10. It's 10. Sorry for handwriting. And the degrees of freedom for sample 2 is 25. Okay? And we indicate that as a subscript of your F. Okay? So we construct this F distribution curve, and then we just plot your F statistic, which is 2.24. And then we also plot the alpha. So the level of significance is 5%. Again, we have to integrate this area and find the location where the cumulative probability is 5%. So this is around here. So this is our cutoff for the rejection. So this is the rejection area, and we can see here that the F statistic is outside the rejection area. Sorry. Okay, so this is the rejection area. Ah, crap. Okay, this area is your rejection area, and this is your F statistic, so it's outside the rejection area. So it means that you will have to accept the null hypothesis, or you fail to reject the null hypothesis. Okay, so in the eyes of statistics, these two variances are the same. Okay. All right. All right. So thanks for listening. This is the Okay, so again, this is just a lecture from the USGS, and just merely modified and um, give a voiceover for this lecture. And these are the references. Okay, some of them I've included in the syllabus. So you have your Davis. You also have your. I think you have your Davis here. All right, so this concludes the lecture on statistical testing.